All right, these are the last two I'm going to do for you, and they happen to be ones that were assigned to you. And number 35, we don't have as much information as some of the other problems that I hope you watched before this one. But we have this radioactive chemical, radium-226, and it decays to half its substance in 1,590 years. What is the annual decay rate? Express the decimal result in 4 significant digits and the percentage to 2 significant digits. All right, so I wrote down a couple variables. So we're going to let the quantity be the amount of radium, and T equals the amount of years. And typically we would go for a function. Q of T equals A B to the T power. We don't know A because we don't know the starting amount. Well, we've used this notation, Q naught, as a variable. Since we don't know what it is, we're going to call it Q naught. That's the starting amount. All right, I'm going to write down a couple of facts, or at least get some organization on thoughts. When the time is 0, the amount that we're starting with is called Q naught. That's what we're calling it. And it said that half of this is going to go away. Half is left. In 1,590 years, we're going to have 1/2 of that Q naught. Okay, so there's some missing information here, but we still have quite a bit that we can work with to make an equation, because this would correlate to our starting value. So I don't know what the starting amount is, but I can at least write it as a formula. And this gives me a point that I can plug in. So I don't know how much of the half amount is left, but I have a formula for it. So I'm going to plug in that formula, and then there's quite a bit that we can solve at that point. So I'm going to plug in the output right here, and I will have 1/2 Q naught equals, and then the A, that is the starting amount. Now we don't know what it is, but we're calling it Q naught, times B, and the power, when I plug in, is the 1,590 years. All right, so I'm going to start solving. Let's divide Q naught on both sides. It turns out that we don't need to know how much is the starting amount, because the equation simplifies without it. And now I can solve for B. So B is going to equal 1/2. I have to do 1 over 1,590 as my power on both sides. All right, over in the calculator you can see I've loaded up the expression that I want to evaluate. Now, because I have an older operating system here, we have to use a lot of parentheses when we have fractions. And my exponent is a fraction, so you can see how I put a parenthesis at the beginning and the end of this. And when I calculate, I am getting B. Now I'm going to leave all those decimals in there. I don't want to round off anything until the end, because over here, it says to express the decimal results to 4 significant digits and the percent down to 2 significant digits. So let's find R, because that's what they want us to get. What is the annual decay rate? So we need R. And so remembering that B equals 1 plus R, and it's negative. So really, maybe I should just get my R number and realize that it's decay and use the minus in there, and then I'm going to solve. So I'm going to solve this one by subtracting 1. I'm going back to the calculator and subtract that 1. And there's my negative decay rate. And it has a lot of decimals. So the e to the -4 over here, that's just exponential or engineering notation. Or some of you know scientific notation is times 10 to the -4. So if I have that 3, 5, 8, 4, 6, 6, e to the -4. If I write it as a decimal, that just means I am dividing by 10,000. So I'm going to move the decimal over to get rid of that exponent. So it's -0.1234, 35846. Okay, so there's R. Now they wanted 4 significant digits. So that would make my 4 significant digits all the way out here. And then lastly, we can write down R as a percent. So as a percent, I'm going to multiply by 100 to turn that into percent. So I'd move that decimal. I'm going to have 0, 4, 3, 5, 8%. Lastly, they said to do the percent in 2 decimal digits. So the 2 significant digits would be the 4 and the 3, and after the 3 is a 5. So I'm going to round that up to 0.44%. That gives us the decay rate. It's a really small decay rate. So it's decaying very slowly. That's why it took 1,590 years, because we have a very tiny decay rate. All right, let's tack the next problem, number 38. So I forgot to say this about the number 35. But if you haven't done the homework yet, I encourage you to pause the program and do this problem first. Really challenge yourself. That's how you learn, is by struggling with it. Then work it out as best you can, then watch the video. So go ahead and pause and work it out if you haven't done it yet. But now we're going to go in together and you can check your work. I'm not going to read the whole thing, but I'm going to start dicing it up. I see initial population of this bacteria. That's always a nice thing to start out with. As I read through, I see that it's talking about T is time in hours. And we're looking at a bacteria that doubles in 20 minutes. Oh, so if it's doubling in 20 minutes, that's not the best bet there. So let's make this in minutes. Okay, so if it's doubling in 20 minutes, now I have another fact to work on. It's going to be twice as big as this. So when I have twice that amount, we will have 2,700 bacteria. All right, let's see, we have plenty. We can solve for the model here. So if so far, I'm going to use the function b of t for the model, and I know the starting amount. I don't know b yet, but there's the beginnings of this model. Now I'm going to plug in a point here. I'm going to plug in 20 minutes and divide both sides. And that's going to be simple because it's just double. So we'll have 2 is b to the 20. So if I want b by itself, I'm going to have to take the 2 and do the 1 over 20 power on both sides. I kind of skipped the algebra step there. Now I don't want to round this decimal off. I want to keep the decimal in the calculator as big and full as possible, so I keep it as accurate as possible. Okay, so I set it up in the calculator. We can calculate over here and we get 1.05. So we've got our B, 0.35. They want us to round to 5 significant digits to write an exponential equation. So here's our exponential equation. It is going to be 1350 times 1.035. That's 4 significant digits. Then 2, 6. That 2 is in the 6th, is in the 1, 2, 3, 4, 5th digit, the 5th significant digit. But after it is a 6, so that tells me to round this up to a 3, and I got it to the t power. And there's my model with 5 significant digits in it. And then the last thing, my time, my space is very limited here. I think I'll change colors for that. This almost threw me off because I had t equals hours for a bit. So we got to watch that. So t equaling 3 hours means that we have to plug in 180 minutes. And so we have to come back here and evaluate at 180 minutes. So that is just plugging in 1.0353, raise that to 180 minutes. Let's plug that in the calculator and see what we get. All right, so we get this large number, 695,000 bacteria. So this bacteria is growing quite large now after 3 hours. 695,428 bacteria. I'm going to round it to a whole number of bacteria cells. Okay, so there you go. I hope that was helpful. Study hard on this stuff, and good luck.